Okay. So now we move on to an ellipse. What is if we weren't doing this now, what would you think is an ellipse? How would you describe it? An oval, right? It's longer. It's like a circle that's just longer in one direction than the other. Okay, that's essentially what it is. So we will pretty much give ellipses the same treatment as we did for parabolas. With parabolas, besides putting it into standard form and graphing, understanding the parts, we did the reflective property, right? And for ellipses, we will do kind of eccentricities of orbits. Okay, so the definition, right? All these have a definition that start with the words the set of all points. Right? The ellipse is the set of all points, the sum of whose distances from two fixed points is constant. So if you look at the picture on the left, those 2 points, each one of them is called a focus, and the plural is foci. You say that, foci. So all the points on this elliptical shape here, if I calculated the distance to one focus and then the distance to the other focus, and I added those two things up, I would always get the same number. It's a constant. Okay, an ellipse will be longer in one direction than the other, right? We don't have an ellipse that's it's the same, because what would it be if it was the same? It would be a circle, right? So ellipse has to be longer in one direction than the other. And the direction that it's longer in is called the major axis. Right? The shorter direction is called the minor axis. Okay. The center is the center, right? It's halfway across and along in the short directions. That's the center. And where the major axis intersects with the sides of the ellipse, those are called vertices. In some books, they call even where it intersects on the minor axis are vertices. I think I've seen them called co-vertices or something like that. Actually, different books do different things. I'm tutoring this kid who's a homeschooled kid in Algebra 2. And this homeschool outfit is using a book from 1990. It's 25 years ago. And when we're doing the octants, they do octants in the Algebra 2 books, right? We're doing it at the end of a pre-calculus. They were doing octants back then. But they number the octants completely differently. Like if we did the octants like, right, 1, 2, 3, 4, 5, 6, 7, 8. They're doing 1, 2, 3, 4 all on the positive X, and then 5, 6, 7, 8 on the back. I've never seen that before. But our old Algebra 2 book called these vertices. They're all vertices, right? But this one, only these are called vertices when they ask for them. Okay, so we're going to have two standard equations depending on whether the major axis is horizontal or vertical. Right? And the picture below, I'm going to do 2 slides. One of them will show the horizontal and one of them will show the vertical. But this is the equation, the standard equation. Okay, so the HK in this case represents the center. Right? HK is the center, right in the middle. And you can see in the equation, besides that, the only other letters that you got to deal with are A and B. And from the picture, what you can see is the A is the distance from the center to the vertices, meaning in the length of the major axis, right? It's from the center along the major axis to the side. So this is A, and this is also A. So what's the length of the major axis? From here to here, 2A, right? A is the distance, the long distance from the center to the side. That's A. B is the distance from the center along the minor axis to the side. That's B. Now, the other thing you should notice about the standard form is the right-hand side equals 1. It has to be 1. It's not, if it's not 1, you're going to have to do something to make it 1. Okay, now, a lot of what you see in here is essentially explaining that there is a relationship between the A and the B, and it involves a third letter, which is C. C is the distance from the center to the focus on either side, right? This distance here is C, C, C. So since C is the distance from the center to the focus, and A is the distance from the center to the side of the ellipse, which is always going to be bigger? A, right? And since A is half of the major axis and B is half of the minor axis, which is always going to be bigger, A or B? A, right? So the biggest of the three is A. So there is a Pythagorean theorem kind of looking relationship between A, B, and C. But it's not the Pythagorean theorem, right? It is that A squared equals B squared plus C squared. Since A is bigger than B and C, right, then their squares have to add up to A squared. I mean, it's kind of, it'll remind you of the Pythagorean theorem, but you got to remember it's A squared is on one side. Now, they've rearranged it here to say C squared equals A squared minus B squared, but either way, same thing. Now, C does not show up in the standard equation, but it's part of it. We'll have to use C sometimes to figure out A or to figure out B. So yeah, it doesn't show it. Yeah, it does. There's the focus. There's the focus. So again, the foci are along the major axis. Tyree, you awake? Don't look like it. Ready? So the vertical, did I do that wrong? Just a second. I'm not sure why I did that, but I think I've explained everything I needed to explain on that one. Okay. Not sure. I don't remember why I did that. But. So the vertical would be up and down. Now, this bottom one is the vertical. So since the major axis is vertical now, A is it's a difference in Y, right? Now the B is a difference in X. Now, if you notice the difference between these two equations, between whether it's horizontal or vertical, what's the only difference? Yeah, where do you find the A and the B, right? If the bigger denominator is underneath the X, that means it's horizontal. If the bigger denominator is underneath the Y, that means it's vertical. The first term is always X. The second term is always Y. You don't move those around. You just move the A and the B around, which is exactly the opposite that you do with hyperbola, which we'll see next time. So, the same relationship, whether it's horizontal or vertical, the same relationship between the A, B, and C. A squared equals B squared plus C squared. HK is still the center. Courtney? Okay. So these are the kind of problems we do with this. Find the standard form of equation of an ellipse having foci 0, 1, and 4, 1, and a major axis length of 6. Okay. As always, graph them, right? Before you start doing anything, graph them so you have some idea of what you're looking at. I mean, for the most part, you don't even know, should I be using the horizontal or the vertical until you get some kind of a conception of it. So I'm going to do that. 0, 1, and 4, 1. So 1, 2, 3, 4. So 0, 1, there's one focus, and 4, 1, there's another focus. So is this thing going to open up is this thing going to have a major axis which is horizontal or vertical? It's horizontal, right? Because the foci lay on that line. So we know it's going to be something like this. Where's the center? They're exactly in between the foci, right? So what would be the coordinates of the center? 2, 1, right? Right there would be HK. 2, 1, which is HK. Okay, what are they trying to tell us? They say the major axis length is 6. What did they tell us by saying that? That 2A, the length of the major axis, is 6. 2A equals 6. So what does A equal? 3. A equals 3. So we would know that in order to go to the vertices, then we would have to go from the center 3 to the right and 3 to the left. So this one would be negative 1, 1. This one would be 1, 2, 3, 4, 5, 1. Now, they didn't actually ask us to draw this graph. All they said was find the equation. So which equation do I use? I use the one which has got the bigger denominator is going to be underneath the x. It'll be this. X minus h squared over a squared plus y minus k squared over b squared equals 1. Okay, we know the hk, that's 2, 1. We know that the A is 3. We got to find the B. So how can I find B? Yeah, you need to use that A squared equals B squared plus C squared. What is C? Remember, C is this distance here, the center from the center to a focus, and that looks like it's 2. So we know the A and we know the C, we can find the B. So if A squared equals B squared plus C squared, then 3 squared is 9. 9 equals B squared plus 2 squared, which is 4. So B squared equals 5. Okay, do I need to take the square root of B? I mean, in the equation, it's squared anyway, so there's no, you don't really need to know the B. It's the square root of 5. But in the end, you have to plug in B squared. So now we know everything that goes into that equation. It'll be x minus 2 squared over 9 plus y minus 1 squared over 5 equals 1. That's it. Good. Yeah.
How come for 9 you didn't, since A is 3, why didn't you just put 3? Like on
Here?
5 you didn't put, yeah, like you squared it, but on 5 you didn't.
Well, it's A squared. So since A is 3, I got to square it to get 9.
So the ones you put 5 squared?
No, because we didn't actually solve for B. We just left it at B squared, exactly what we need to plug in. Right? We used this formula, which had a B squared in it. We actually solved it for B squared. You know, we didn't need to go any further because the equation has B squared. Yeah. Okay. So I'm going to show this. Most of the few next slides, I'm just trying to emphasize the completing the square, because you got to do the completing the square. You can't get lost on that. I mean, this is not supposed to be about completing the square. It's supposed to be about ellipses. But in order to, to understand the equation of the ellipse, you got to put it in a standard form, and that may require completing the square. So there's like 3 slides where we're doing the completing the square. So find the center, vertices, foci of the ellipse And they give us the general equation, meaning there's no parentheses. It's got the higher degree terms on the left, the lower degree terms on the right. It all equals 0, right? We need to put it into the standard form. And just following their work, we'll do the next one, but I'm just going to follow their work here just to show it. First, they get the x terms together, right? X squared plus 6x. And then they get the y terms together, 4y squared minus 8y. And the 9 pushed to the other side. Okay. Now, before you can complete the square, you cannot have a coefficient on the squared terms. If there is, you have to factor it out of the parentheses. So from this step, from here to here, they're factoring out the 4 from the first two terms. Right? It's not factor the first two terms, because if you were looking for a greatest common factor between those two terms, it wouldn't be 4. It would be 4y. And a lot of times that's what I see on the page is that you factor 4y out and now you're just totally lost. Don't factor completely. Factor just that number from the first two terms. Okay, once you're at that point, once both of these quadratics inside the parentheses have the a is 1, I shouldn't call it a, but you know what I mean. The coefficient of the x squared and y squared is 1. Now you got to go through that thinking of half the middle term squared is what goes into that spot. Right? Half of 6 is 3. 3 squared is 9. So they added 9 here. But if they add 9 here, you got to add 9 there. Okay. For the second one, half of negative 2 is negative 1. Negative 1 squared is positive 1. Okay. Now, you don't add 1 to the other side because this 4 outside parentheses, you're going to have to multiply 4 times 1. That was actually a 4, not a 1. So we add 4 to the other side. Now, these are relatively simple trinomials here. I mean, you could just look at it as a factoring problem, right? That's x plus 3 times x plus 3, or x plus 3 squared. This one is x minus 1 times x minus 1, or y minus 1 times y minus 1, or y minus 1 squared. But remember, it's not always that easy. And if you just keep in mind, it's always whatever the half of that number was, that's what goes there, including the plus or the minus. Like this one, half of negative 2 was negative 1, so it's minus 1. Now, if you got to that line right there, right, this one, it does not have a 1 on the other side. So in order to make it in the standard form, we got to divide by 4. You know, you couldn't subtract 3. If you're thinking, well, why don't I just subtract 3? That would make a 1. But then you'd have an extra term on this side too, and you can't deal with that. So divide by 4. Right? When you divide this one by 4, you get a denominator of 4. When you divide this one by 4, it cancels the 4, and you just get a 1. Right? And then on this side, you get your 1. Okay, now it's in the standard form. And is this going to be a horizontal or a vertical? How do you tell? The bigger denominator is here, so it will be horizontal. Since the bigger number is underneath the x is a horizontal coordinate, that it'll be longer in that direction. They actually took another step and wrote it as 2 squared, so you could tell that a is 2 and b is 1. Okay, so it said find all that and then sketch. Well, what have we found so far? We've got our equation, and from that, we know h, k, a, and b. But in order to find the vertices and the foci, you know, we're going to still have to do a little bit of work. I don't remember if I put that on the next slide. Yeah, I think I took that and I copied it over here. So now let's figure all this out. First, I'm going to start the sketch. It's going to be the vertex is -3, +1. So draw it a little longer in that direction. -3, +1. Right, that's the HK. I'm not going to label it yet. Okay, then I'm going to go in the X direction. I'm going to go 2 to the left and 2 to the right. Right, because A squared equals 4, so A equals 2. So I went 2 to the left and 2 to the right. And then in the minor axis direction, right, b squared equals 1. So b equals 1. That means I'm going to go up 1, down 1. I mean, with just those 4 points, I can sketch the ellipse at this time, right? I mean, there's no other points are going to help us draw this thing. So just go ahead and draw your ellipse that goes through those 4 points. And now I can label some of these points, right? That point, the center, HK, equals -3, 1, right? The vertex is -5, 1. This vertex is -1, 1. And now I need to put the foci in there. Okay, what value do I need so I can place the foci in the right spot? I need the C, right? And how am I going to find the C when I know A and B? I use that Pythagorean theorem looking thing, which is A squared equals B squared plus C squared. So A squared is 4, B squared is 1, so 3 equals C squared. Now in this case, we kind of need the C. So take the square root. C equals the square root of 3. And the square root of 3, in terms of graphing, just so I can place it in the right spot, I'm going to approximate it as a decimal. It's around 1.7. So I'm going to have to say C is approximately 1.7. So from this point here, the center, I'm going 1.7 to the right, 1.7 to the left. These are the foci right there. And the coordinates for those points, normally the way they write that is like this. Starting at the center, -3, plus or minus the square root of 3, comma, 1. So we don't actually use the decimal to figure it out. Just say, start at this point, go square root of 3 to the left, square root of 3 to the right, comma, y is 1. Okay. Okay. So this one will do. This is actually the checkpoint underneath that. So they don't have an example in there, but more practice. So again, what would I do first? Get the x's and the y's together, throw the constant onto the other side, right? So I'm going to write x squared plus 36. Oh, that was wrong. I should have written 9x squared plus 36x, right? Leave a space. I don't even, it's actually not necessary yet, but 4y squared minus 8y equals -4. Okay, then what? Factor out the coefficients of the squared terms. Okay, so for the first set of parentheses, it'll be 9 times x squared plus 4x. And the second, 4 times, right? Okay. What am I going to add into this position right here? Half of 4 is 2. 2 squared is 4. But if I put a 4 there, what am I going to add to the other side? 9 times 4, 36. Okay. How about this one? What am I going to add into this position? Plus 1. So what do I add to the other side? 4 times 1 plus 4. Go back to blue. Okay, what is the next? It should be 9 times, and what is it that goes in parentheses squared? X plus 2. And what goes in the next set of parentheses? Y minus 1. and add everything up on the right-hand side, and you get 36. Okay, is that in the standard form? What do we have to do? Last step. Divide by 36, because we need a 1 on the right-hand side. So divide 36, divide 36, divide 36. So this will be x plus 2 squared divided by 4 plus y minus 1 squared divided by 9 equals 1. Yeah, it looks like that it's going to be vertical. So let me see if I can do this. Because I don't think I've got an extra slide there. Do I? No. I'm going to see if it lets me copy this to the next page. Sometimes it does. No. Okay, edit, copy, and then insert page after. Edit, paste, and erase all that stuff up there. I think that'll be good enough. Close enough for government work, as I say. Okay, what is the center? -2, +1. Okay, is this horizontal or vertical? Because, yeah, because that's bigger, then we know it's going to be longer in the y direction than it is in the x direction. So if this is the a squared, then what is a? 3. And if this is the b squared, what is b? B is 2. Okay, now we know that ultimately we need the c so we can graph the foci. So we need to calculate that, right? That'll be a squared plus b squared, a squared equals b squared plus c squared. So it would be 9 equals 4 plus c squared. So c squared equals, again, 5. And c equals the square root of 5, which is approximately 2.2-ish. That'll help me to draw it anyways. So I think we've got everything we need to go to a graph, sketch a graph. Let's see, the center is at -2, 1, so that's quadrant 2, and it's a little bit above, so -2. So the vertex is at -2, 1. We're going to go up 3 and down 3, up 3 and down 3. What are these 2 points? They're the vertices, right? And then we're going to go left 2 and right 2, left 2 and right 2. Right, those 4 points give us the sides of the ellipse. And now we need to put the foci in the right spot. We know that they are going to be somewhere along this major axis. I'm going to go 2.2 up and 2.2 down. Right, so about there and 1, 2, about there. Okay, now I'm going to label all those points. Right, this is -2, 1. This one, if I add 2, that is going to be 0, 1. This will be -4, 1. Oh, actually, I didn't need to label those, did I? Those are not the vertices. I needed to go up 3, so that was -2, 4. And this one was -2, -2. And the foci, I'm going to write them off because they're a little more complicated. Foci are Again, using the same convention that I did before, they have x coordinates of -2, and the y coordinate will be starting at the center, 1, and then I'll go up and down square root of 2, square root of 5. So that'll be 1 plus or minus the square root of 5. I think that's everything we're asked for. Don't know what else it could be. We good, Morgan? Morgan's good. Okay. Eva? You good? Okay. And I'm just going to show one more of the completing the square. This is their example 3. So, I mean, if you're having trouble with completing the square, you know, look at some of these. I can't imagine being any more clear about how to do this one thing. We don't want to get hung up on this thing. So you could, let's see what they do. They started with the general equation, no parentheses, terms in order. They get their x's together. They got their y's together. It looked like we had to factor one of those because there was a 4x squared there. They took out a 4, right? What was left? X squared minus 2x. Okay, then they had to go through the same thought process. What are the what is half of -2? -1. Squared is 1. What is half of 4? 2. Squared is 4. But if you add a 1 here, that's really 4 times 1. If you add a 4 there, it's really 4. So now you can say this is a perfect square trinomial. It's x minus 1 squared, and this is y plus 2 squared. Now, is that in the standard form? No, you would still need to divide by 16. I don't remember why I didn't do that, because I don't think I wasn't going to do this whole problem. I was only looking to give you another example of completing the square. Right, so this one would be x minus 1 squared over 4 plus y plus 2 squared over 16 equals 1. That's standard form. Right, got to have a 1 on the right. Okay, and now the last is, this is an example that they're talking about orbits. And, you know, when it comes to the applications of ellipses, you know, if you look in their word problems, there's always a few different ones. Sometimes they're kind of a stretch. But the truth is that ellipses are the shapes of the orbits of the planets, of the moon around the Earth, things like that. And, you know, it's very interesting how we even discovered that kind of thing. You know, it goes all the way back to, you know, who's the first guy that said that the sun was the center of the universe and not the Earth? Who was the first guy? Did they teach you anything in a science class, Sandy? Aristotle. Not Galileo, but that's a good guess. Galileo was supporting somebody that came about 50 years before him called Copernicus, right? Copernicus is the one that said, you know, the Earth is not the center of the universe. Galileo comes along like around 50 years later, you know, at a university just down the road from where my wife's family is from, and uses a telescope, which he didn't invent, but it had been invented in Holland. And he understanding how they put it together, he put one together. And he trained that telescope on the planets, on Jupiter, in fact, and he could see clearly that there were moons going around Jupiter. And that was kind of like the last straw. Okay, clearly not everything goes around the Earth, because look at those moons going around Jupiter. Now Jupiter has many moons, but those 4 moons are called the Galilean moons still today. Okay, so he comes along and does that. Now, people with their telescopes now trying to put together the right puzzle, which is that the sun is the center and we're not, we're actually going around. They start to piece things together, but if you can imagine, the distances involved are huge. And they don't have calculators, and they don't have computers. But what was invented right at that time, right in the nick of time, was logarithms. And logarithms simplified the multiplication into addition. You ended up with tables and tables of logarithms, which were the exponents you would raise a particular base to get a number. And then when you multiplied, all you had to do was add the exponents, right? Made that process so much easier that they were able to start actually doing calculations. And they're able to do calculations that would tell them, you know what? It's not a perfect circle going around. You know, it's actually a little bit longer one direction than the other. I mean, look at the orbit of the moon. It's in the long direction, it's 768,800 miles from the center to the side, right? That's like our A. In the short direction, it's 640 miles. I mean, that's like 99.9% of that right there. And yet they were able to determine that using their telescopes, science, logarithms. And, you know, the guy who's given the most credit for that is a guy named Kepler. So in this problem here, right, it says the moon travels about the Earth in an elliptical orbit, right, with the Earth at one focus, right? What's at the other focus? Nothing. But the Earth is at one focus, right? The major and minor axes, right, have lengths of, in fact, this is the entire major axis, not half of it. And this is the entire minor axis, not half of it, like I just said, right? Find the greatest and the least distances from the Earth's center, right, to the moon's center. And they've labeled it right there. They're showing you it'll be the least distance when it's right there, right? It'll be the greatest distance when it's right there. So what would we have to determine so we could figure out this distance or this distance? I mean, we could easily find half, right? You could divide that by 2 and get the half. But what would you still need to know? You would need to know that little distance right there. And what does that distance represent? From the center to the focus, which is the C, right? We need to know the C. So then we'll just add or subtract it from that. And we can easily find that. I'm going to use my calculator here. Easier than poking around on the screen. Clear. Okay, so let's see. Our A is 768,800 divided by 2. 768,800 divided by 2. 38400. 384,400. Our B is half of this. 767,640 divided by 2. 767,640 divided by 2. 383,820. Okay. Now, in order to know the C, we've got an equation for that, right? A squared equals B squared plus C squared. So C is going to be, and I'm just going to do this in one fell swoop. C equals the square root of this squared, 384,400 squared plus 383,820 squared. So let's do that. Second square root, 384,400 squared plus 383,820 squared. I'm getting 543,213. I'm going to round it off, 214. So C equals 543,214. Right. So in order to find the long, I took the square root already. Yeah, I put it in as a square root. In order to know this distance from here to here, I have to take half of the 768 and, oh, sorry. Yeah, I have to take the half and then add that number, right? And then if I add that number and I subtract that number, I'm going to get this. So let me do that. 384, 384,400 minus 5. Oh, that doesn't seem right, does it? Oh, you're right. Silly. That should have been a minus. Thank you. Yeah, it should have been 21,108. Don't you got to catch me on that stuff. Okay, minus 21,108. Right, so now do this number plus that and this number minus that. 384,400 plus 21,108. 405,508. 405,508. And the other one would be 384,400 minus 21,108. 363,292. Okay. Now, how much? I mean, that's, as you say, if you looked at that with the naked eye, as they would say, it kind of looks like a circle. It would be hard, you know, if somebody just showed me that shape, I'd think it was probably a circle. How distorted, how much longer it is in one direction than the other, how much unlike a circle that it is called the eccentricity. Right? Oh, I guess I already did that. The eccentricity. And the way we calculate eccentricity is simple. It's the C divided by the A. Right? Some of the homework problems, besides asking you to graph and label all this stuff, it says find the eccentricity. At that point, you've already found C and A, so just divide them, and that's it. You can notice that the closer the foci are to the center, that means the C is really small. And then when you divide it by the A, you're going to get a number that's really close to 0. Right? The farther away from the center that the foci are, that means it's getting closer to the A, and the number approaches 1. Now, could it ever actually equal 1? No, it can't ever equal 1, but it can get close to 1. Could it ever equal 0? No, it's going to be somewhere in between the two. Now, we could calculate the C divided by the A for the moon, right, the one we just did, right? That would be, I think, I don't need that. For the moon, it would have been 21,108 divided by 384,400. And we'll see what kind of number we get for that. .0549. Right, that's the eccentricity of the moon's orbit around the Earth. Now, if you compare that to, I just did that. If you compare that to the planets going around the sun, right, we just said the moon was 0.0549. I mean, look at the Earth's orbit around the sun. It's even closer to a perfect circle, 0.0167. Which is the least of all these? Which one has the orbit which is closest to a circle? It looks like Neptune is first. And then actually, no, it's this one. Venus, and then Neptune, and then the Earth. Which one has the more elongated orbit of them all? Yeah, Mercury 0.2, and that's that. So eccentricity, that's what it is. It's part of some of the homework problems. It does kind of get at the one thing that we kind of think we know that's practical about ellipses is the orbits. So we'll add it. It's a simple calculation. And these were odds.